The first big problem in calculus is the problem of calculating what we call instantaneous velocity. And when you see that phrase, I want you just to think of speedometer speed. So when you look at the speedometer in your car, it tells you exactly how fast your car is traveling right at that exact moment. That's something we just take for granted, but back in the day, that was a huge mathematical problem, and people like Galileo couldn't even really figure out of how to conceptualize or wrap their heads around figuring out what we're going to call an instantaneous rate of change. So before we get there, we'll start with average speed, which is very easy to calculate. I'm using the words speed and velocity pretty interchangeably. So my example is that you drove 120 miles in 2 hours. What was your average speed? You probably just did that in your head. Maybe you didn't even really think about how you did it, right? But here's what you did. So you did 120 miles divided by 2 hours is 60 miles per hour, right? So in other words, rate is distance over time. And in general, that's what we're going to do here. We're going to take the change in one quantity and divide it by the change in another quantity, distance divided by time, and that's how we're going to get these average rates. New example. So if we drop a rock off of a cliff, it will fall 4.9 t squared meters in t seconds. That's a very old formula figured out by Galileo just by dropping stuff off of things and timing it. And that's still the number we use to this day, 4.9 for in meters. So we're going to go up to a 490 meter cliff and drop a rock off of it. And we're going to answer some questions. So the first one is, how long will it take to hit the ground? We can do that with basic mathematics. We say, okay, it's going to fall 4.9 t squared meters. We want it to fall 490 meters, so we just set those two equal to each other. And it's a how long question, so we're solving for t. A little bit of algebra. The answer t equals plus or minus 10, while generally correct, doesn't make any sense in this context because it can't be minus 10. So the answer is t equals 10 seconds. Same thing, if we want to figure out the rock's average speed, we just take how far it traveled, 490 meters, over how long it took, 10 seconds. 490 meters in 10 seconds is 49 meters per second. So the problem we have to deal with now is that the rock sped up, right? It wasn't going 449 meters per second the whole time. It started off going slow and sped up, right? That's how gravity works. And then it hit the ground. So it was going pretty fast when it hit the ground, probably. Not so fast after 5 seconds, right? It's barely going at all at the moment you drop it. And we need to get a sense of that. And it turns out we need to do some stuff before we get there. So when we talk generally about something changing over time, we use the term average rate of change rather than average speed. If we talk about, let's say, like a population of deer growing or something, you wouldn't use really like the word velocity for that. So generally, we can just say rate of change. So when we talk about that instantaneous speed, that speedometer speed that we're trying to figure out, the math term for that is instantaneous rate of change. So that's a phrase you're going to hear quite a bit in the next couple of weeks, because that's really the main thing we have to figure out is how we even have a concept of that instantaneous rate of change. So now, as we do in math, we take a real world problem and we break it down just to numbers, right? To just cold hard numbers. So we're just going to look at the function x squared, just a good old parabola, and we're going to figure out the average rate of change of that thing over the interval 1, 3. So from x equals 1 to x equals 3. So here's what that looks like. Let's have some intuition about this. It went up, and it went up kind of a lot. So this is a function that's increasing, and it's increasing pretty fast. So that average rate of change is going to be positive, and it's not going to be a small number. It's going to be a relatively big number because the function went up quite a bit in a little, 2-second, we'll say, time period. But the math to do is exactly the same. We're just going to do the change in one thing, and we're going to divide it by change in another thing. So here's the general way to do that. We're going to take how much the y's went up and divide it by how much the x's went over. So if you look at the graph, it went up 8 and it went over 2. So the math is easy. I promise this class gets much harder. So that little triangle thingy you see is delta. So write that down because you're going to see that letter again. That's a Greek letter, delta, and it means change in. So at some point somebody decided that's the mathematical symbol for change in, right? So that just means change in y over change in x. Delta y over delta x is how we say that. So we just take the difference in the y values, right? It went from 1 to 9, so it went up 8, divided by the difference in x values. So it went from 1 to 3, so it went over 2, up 8, over 2, 8 divided by 2 is 4. And there are no units here. You can think about that as miles per hour or meters per second or whatever. It's just y's per x. So since we're just using numbers per number, we don't really write units. But obviously in like a story problem, we would. So that little calculation we just did hopefully reminds you of something from algebra class. It should remind you of y2 minus y1 over x2 minus x1. And if you're wondering why there's that little dotted line connecting the 2 points, right, that should remind you of, oh, that's just slope. And that's in fact true. That thing we just figured out, the average rate of change, is exactly the same calculation as figuring out the slope of the point, or I'm sorry, the slope of the line connecting those 2 points. That line has a name. It's called a secant line. So anytime we draw a line connecting 2 points on any curve, we call that the secant line between those 2 points. And figuring out the average rate of change for a function between those 2 points is exactly the same calculation as figuring out the slope of that secant line. So that is a very convenient visual for us that we're going to come back to. Okay, so here's what a tangent line is. This doesn't really have anything to do with the tangent function from trigonometry. It's just what it's called. So to be a tangent line, it has to satisfy these 2 requirements. And once you see the picture in a second, it's a lot easier to explain if you just look at a picture of it. So the requirements are a tangent line. It touches a curve at exactly 1 point, right? So you're going to see it like barely glances off a curve, and then it has the same direction as the curve at that point. So we want to look at lines that are going in the exact same direction as a curve at different points along the curve. These are tangent lines, right? So just notice a couple things about them. So you see what I mean when I say it has the same direction as the curve? When the curve's going up, the lines are going up. When the curve's going down, the lines are going down. The faster the curve goes up, if you look at those red lines over there on the right, the steeper the line is, right? So the slope of the line matches up with the direction of the curve at all those various points. So at every point along the curve, there's a different tangent line, right? Tangent lines are unique to whatever point you're at on the curve. So they move around. As you move, think about like moving along that curve and picture the slope of the line changing. So the red lines have positive slope, and those happen where the function is increasing. The blue lines have negative slope, and those lines are where the function is decreasing. Remember, you read it from left to right. The green lines are important. If you think about those points where the green lines happen, so we say that that line is tangent to the curve there at that specific point. The word for those points are called local maximums and minimums. One of them's a max, one of them's a min. And if you think about what those lines should look like, well, they're horizontal. And the slope of a horizontal line is 0. So a kind of big concept we have is we can actually find those points now by literally finding any points along the curve where the slope of the tangent line happens to be 0. Then we know we're at a max or a min. We really don't have a way of doing that without calculus. So that's way down the road. Okay, so the important thing right now is just for you to visualize what a tangent line should look like. So if I gave you a curve and a point on it and I said just draw the tangent line, you should be able to do that, right? We're not to the point where we can find equations for them or we find exactly what the slope is, but you should just visually understand whether a line is a tangent line or not. And the big important thing to keep in mind for now is that whatever that slope is, whatever that number is, that is exactly equal to the function's instantaneous rate of change. So it's a convenient visualization for that idea of speedometer speed. The idea of, okay, this thing is going exactly this fast at exactly this moment when the speed is constantly changing all the time, like it is in your car or like it is when you drop something off of a cliff. So we can do stuff with tangent lines, but for right now, it really is just like a nice way to visualize the thing that we're talking about. So we now need to figure out, okay, well, what are these numbers? What are these slopes? So we're going to do it, and we're going to do it in a pretty sloppy way, but just to be able to get a concept of the process and how we find it in a non-sloppy, calculus type of way. So we're going to go back to our parabola, x squared, and we're going to focus on the point 1, 1. So visualize what that tangent line should look like in your head, right? Draw it on whatever you're taking notes on. It should go through that point. It should be sloping upwards, and at the point 1, 1, it should really match up to the curve, right? It should barely glance off the curve and match up to it as closely as possible. So here's the first thing we do is we take a generic point, x comma x squared. So instead of looking at the point 39, that was a specific point along the curve, we're going to look at a generic point along the curve, and every point on that curve has the form xx squared, right? So it could be 39 or 416 or 525 or negative 2, 4 or whatever. It's just a generic point that sits on the curve y equals x squared, and it looks like that. So the first thing I want you to do is picture sliding that point around. 1, 1 is fixed, right? 1, 1 isn't going anywhere. But the generic point, xx squared, we could slide down close to 1, 1. We could slide back up the other direction. It doesn't have to be over to the right of it. It can be anywhere. It can be anywhere on the curve. So that's now mobile, and we can slide it around because it's a generic point. So I drew that little secant line there. The slope of the line that connects those 2 points is the change in the y values, which is x squared minus 1, over the change in the x values, which is x minus 1. That's pretty important. Be sure you're comfortable with how I got that expression, x squared minus 1 over x minus 1. That's a generic expression for the slope of the secant line between the point 1, 1 and just any other generic point that sits along that curve. And we're going to work with that expression, and eventually we're going to do algebra with it. And it's okay to look ahead and think, hey, couldn't I maybe factor that numerator and then simplify it? Yes, you can. And I'm not there yet, so I'm going to deliberately not show you that, but I will show you later because we need a very important concept called limits. Okay, so that's the expression we're going to work with. That's a generic expression for the slopes of secant lines, specifically between 1, 1 and anywhere else. So if you look at that expression and say plug in the number 1, you get 1 squared minus 1 over 1 minus 1, which is 0 over 0, which is undefined. We call that an indeterminate form in mathematics. And you know that, right? You can't even divide 0 by 0. And that should make sense because by doing that, you'd be trying to find the slope of the line between a point and itself, which doesn't make any sense. Another way to look at that is you're trying to figure out the average speed of something, but no time elapsed. So it's like it didn't move and no time elapsed. So it traveled 0 in 0 time, so that really tells you nothing. So that's our kind of first big problem, is how we get around that. How we look at things that are close to 0 over 0, but not quite. So here's the initial idea. We're going to plug in a number very close to 1. And I'm just randomly going to pick x equals 1.1, right? That's just a number that's close. That's just a point that's close to our other point. So the slope of the tangent line between 1, 1 and then 1, it's 1.1, 1.21 is that, right? It's just changing. It's just plugging 1.1 in for x, and we get 2.1 for the slope of that secant line. Back to the car analogy, what we're essentially doing now is if you were to take how far a car traveled over 0.1 seconds and found its average speed over 1/10 of a second, that would be really close to the actual speed of the car, right? It couldn't change that much in 0.1 second, so that would be a good way, if you didn't have a speedometer, to figure out exactly how fast a car was going, is to find the average speed over a very tiny time interval, and that's what we just did. When we zoom in, that's what that looks like. I zoomed way in on the curve, and if you look between those 2 points, that straight line, which is the black thing, is extremely close to the curve, which is the green thing. They match up very well. So that looks like it's very close to what the actual tangent line should look like. If we were to zoom back out, it would be like indistinguishable from it. So what we can do is we can go even closer, because we're just doing math here, right? We can use x as 1.01 or 1.001, right? That would be like the average speed of a car over 1/1000th of a second. We could theoretically do that, and we're saying, right, you see what I'm saying? It would be very close to that instantaneous velocity, that speedometer speed. And the idea now is, as we get closer and closer and closer, right, we can't plug in 1, we can plug in anything close to 1. The closer we get, the closer that little expression is going to be to the truth, to the number we want. So I'm going to make a table of values. It would be tedious to keep plugging in 1.001, 1.0001. If you've never used the table feature on your calculator, I don't really have a great way to show you my calculator screen right now, but I will figure it out. But maybe look it up on YouTube. All it is a spreadsheet. So if you're comfortable making Excel spreadsheets, do that. That's all I'm going to do right here. So we're just going to make a table of values for what we get when we plug in numbers that are close to 1, rather than do a bunch of tedious calculations over and over again. So here's what that looks like. X values are the left column. What that expression equals is the right column. A couple important things. When x is 1, this doesn't compute, right? Because it's 0 over 0. So your calculator doesn't know what to do with that. It's just going to return an error because it's dividing by 0, right? It's just going to say error, and that's right. But if you look at those numbers in the right-hand column, they're converging, right? And the concept of convergence, that means a specific thing in mathematics, and it's important to what we're looking at right here. So If that error was like an asymptote in the function in the graph, right, those numbers would veer wildly off to like infinity, but they don't, right? They don't. And when you look at that error, what I'm going to ask is, okay, what number do you want to put there? If you had to stick a number in there in that error, what number would you stick there? In other words, what does the function want to be there? What number should be there? And I think we could all agree that that number is 2. There's a 2 that should go in that little error box there, right? That's not proving anything. It's just intuitive. The number 2 should be where that error is. So that is correct. That is the number. The number 2 is the slope of the tangent line to our parabola x squared right at the point 1, 1. Again, that's not proof. That's not how we're going to do it. That's just guessing by looking at numbers very close to 1 and saying, okay, as we come at it from either direction, those numbers in the right column want to be 2, right? From either direction, they are converging uniquely to the number 2. Okay, so put a pin in that. We're recall point slope form from algebra class. So what we're saying is at the point 1, 1, our tangent line has slope 2. So remember we wanted an equation for the line so we can actually graph it. So here's that old m times x minus x1 equals y minus y1. That's called point slope form, and you are definitely going to need it. So recall that. With just a little bit of rearranging, we get point slope form for it, right? Mx plus b. So that's it. That's our tangent line is 2x minus 1. And when we graph the line 2x minus 1 together with the curve x squared, we're hopefully going to see like that's exactly what a tangent line should look like. So you know it's the tangent line, right? They have the same direction, but it looks very right. And if you were to zoom in, if you have this graphed on your calculator, which you're going to have to do at some point too, zoom in on the point 1, 1. Because the more you zoom in on it, you're going to see that the line and the curve become almost indistinguishable from each other. And they will become indistinguishable. So that's a visual check to know like, hey, I'm right. I do have the right number yet, right? Because what we did just now was just guessing. So that's not calculus. But I want you to understand, I just want you to be able to visualize what a tangent line is supposed to look like. And the way that number, that slope 2, tells you exactly how fast the curve is going right at that certain point. And we want a general way to be able to do that for any point on any curve. And we will. Let's do the same exact move, but with the rock. So we're going to go a little faster now. So we dropped a rock off a cliff. Doesn't matter how high the cliff is. We want to find its speed at exactly 5 seconds. And the way we're going to do that is by taking the average speed of the rock from 5 seconds to, let's say, 5.1 seconds. Because that average speed over 1/10 of a second has to be very close to what the actual instantaneous velocity is. So we're going to go with 5.1 seconds. We're going to go with a 1/10 of a second. So in that 1/10 of a second, how far did it travel? Well, it's the same as before. We go the distance it traveled over the amount of time. So after 5.1 seconds, it went 4.9 times 5.1 squared. At 5 seconds, it had traveled 4.9 times 5 squared, whatever that is. And then the time elapsed is just 5.1 minus 5, which is just 0.1. So punch all that stuff into your calculator. What you get is 49.49 meters per second. So whatever the actual speed is at t equals 5 seconds, it seems like it's got to be very close to that. So let's look at the generic expression. If we weren't using 5.1, if we're just using t, So any other time, 6 seconds, right? 5.2 seconds. You could go backwards in time too, 4.9 seconds. That's the generic expression for its average speed. So just like we did before. So it's 4.9 t squared minus 4.9 times 5 squared over t minus 5. Looking ahead a little bit, you could simplify that expression into that. And then look at that new expression we have. In particular, look at t squared minus 25. Do you want to factor that? I hope you do. You will. So to do this correctly, to actually use calculus to find the speed, which we'll be able to do very soon, that's how you do it. You do some algebra. But we have to talk all about limits before we get into that. I know you want to just get it over with, but we're not quite there yet. So I've just made another table of average velocities of the rock from 5 seconds to times that are very close to 5 seconds. This is just an Excel spreadsheet. Your calculator can absolutely do this. Look up how to do it. So we're getting as close to within 100th of a second, right? So from 5 seconds to 5.01 seconds, the average speed of our rock was 49.049 meters per second. So that's the average speed of this thing over 100th of a second. And right, if you look at the numbers in that right-hand column, they are converging. They're not just going wild. They are approaching a specific number. And you're just going to have to take my word for it that that number is 49. It's not as obvious. The number that we would stick into that error box is 49, and that is exactly right. That is the exact instantaneous velocity of our rock right at time 5 seconds, 49 meters per second. Okay, so what we're going to see in all these expressions, all these average rate of change expressions, is there's the place where we want to stick something in for it, we get 0 over 0, right? So these functions have holes in them. These aren't called asymptotes, they're called holes. That's the actual term for it. Hopefully you have seen those in algebra class before. So what we see at those holes is it's just like we just took a little pinprick out of the function. So it just jumps over a number. But there is a very specific number that the function should be there or wants to be there, right? It's not like an asymptote where it goes to infinity. When you do 0 over 0, it's still undefined and it's indeterminate, but there is numbers that it should be. So we need to talk about those numbers, and we need to find them. So these numbers we've kind of been dancing around, these are called limits. So we say that the limit of the function right there at t equals 5, as t goes to 5, is 49. And limits are the central concept of calculus, which without the concept of limits, you don't have calculus. And that was the big breakthrough by Isaac Newton and some of his, I guess, less famous contemporaries, was in figuring out how to do math with stuff where you can't calculate it directly, where you look at what happens near it, and you look at this concept of convergence. So obviously we can do it using actual math, not just looking at tables and guessing. Let's go back to x squared and the 0.11. So this is pretty important. We're going to look at that secant line, that black line, between the 0.11 and just some generic point x squared. So we're going to do exactly what we did before, just this is more generally, we're going to define some concepts. We're going to take that point x squared, right? So that's our expression from before. That's the slope of the secant line between a generic point and the specific 0.11. So we can plug in anything we want for x. And now we're going to grab that point x squared and we're going to slide it along the curve. We can put it anywhere we want to put it. And in particular, we're going to take it and slide it as close as we want to the 0.11. When we saw before, when we slid it close to the 0.11, the slope of that line was approaching 2. The closer we slid it to 1,1, the closer that expression got to being exactly equal to. And that number is the slope of the tangent line. It is 2. So just picture sliding that thing over and the slope of that line changing. It could come from either direction. We saw that in the table. And what we say is, okay, as x approaches 1 from either direction, the slopes of those secant lines become arbitrarily close to the number 2. Arbitrarily is a big calculus word because it just means we can get it as close as we want to 2. If we get it to 2.01, all we have to do is slide x a little bit closer and we can get it to 2.001. We can get it to 2.000001, right? We can't get it to 2 because there's a 0 over 0 in there, but we can get it as close as we could possibly want it. That's what arbitrarily means. Okay, so here's how we say that for real. The limit as x approaches 1 of x squared minus 1 over x minus 1 equals 2. So how I've been saying, okay, what number should go there? What number wants to go there, right? Where is that little hole? This is the real word for that. So that number is the limit. This function never actually equals 2, right? But as x approaches 1 from either side, that's important, it has to be from either direction, that function can be made arbitrarily close to the number 2. The limit as x approaches 1 of x squared minus 1 over x minus 1 equals 2. I'm emphasizing this because this is where we're going to spend our time for the next little foreseeable future. So here's the notation for that. Okay, so that looks like a bunch of stuff. So for right now, I need you to just stare at that and then stare at that sentence. The limit as x approaches 1 of x squared minus 1 over x minus 1 equals 2. That's just how you write that in math. That's the mathematical notation for that sentence. So it's pretty important that you wrap your head around that. We've got plenty of time and examples to do that. One note about the notation is the little arrow under the limb where x is approaching 1, that arrow points to the right, but it actually means from either direction. So as x comes from either direction, as that point approaches that other point from either direction, it has that limit has to equal 2. It can't be two different things. If it's two different things, then that's called a one-sided limit, and don't worry about that. So just the arrow pointing right is a tiny bit misleading. The arrow can point either way. X can approach 1 from either direction. So just, if that looks new, you just get used to reading that. Just read it to yourself over and over again. That sentence and that mathematical expression mean the same thing. Looking at that same concept again, just on a table, that phenomenon where from either direction those numbers are converging to 2, that's just how you write that phenomenon. That's how you say, so what I've been saying, okay, what number should go there? The number 2 should go there. That's how you really say that. The limit as x approaches 1, right? That the x column is approaching 1 from either direction, and the other column is approaching 2. That means that that's the unique number that should go there. So in the future, that's what I'm going to say. What's the limit? What's the number that should be there? What does the function want to be? That's what the limit is. So without that concept, we wouldn't have any calculus. And without calculus, we wouldn't have anything else, really. So it seems minor, and it really is just a tiny little hole in the function where 0 gets divided by 0. But it gives us the concept for all that stuff, which is all of continuity, anything that changes over time, like a curve, any sort of concept of instantaneous speed, and then even areas and volumes of curved shapes. We don't have any of that stuff without the concept of